Fermat's little theorem is a really nice fact that lets you find that some power is 1 modulo a prime, even though the power is very big. For example, when I look at this that I've just written here, this is 7 to the p minus 1. P is 19, p minus 1 is 18. Oh, so this is very easy. This is 1 mod 19. Wait, there was something else that we were trying to do in this mini course. We were often trying to find the multiplicative inverse of a number. We've just said that 7 to the 18 is 1 mod 19. So 7 times 7 to the 17, well, that's 7 to the 18, is 1 mod 19. That's interesting. What that means is that the multiplicative inverse of 7 is 7 to the 17. This, if I could do this, this would be the multiplicative inverse of 7. It doesn't just work for 7. I can use anything. If I wrote something else, like 8, well, 8 times 8 to the 17. The beauty of Fermat's little theorem is that's 8 to the 19, which is 8 to the p minus 1. So that's 1 mod 19 as well. So the multiplicative inverse of 8 is 8 to the 17. What this means is that I have another way to find multiplicative inverse. The way that we did it last time. Last time we did multiplicative inverse using the Euclidean algorithm. And that worked. It might have been a lot of subtraction, but it worked. We now have a new way. Another way to get the multiplicative inverse of something, mod any prime, is just take it to the power of p minus 2. There's a bit that you might be thinking, though, which is, isn't this hard? If you told me the multiplicative inverse was 7 squared, I can do that fast. But I'm telling you that you need to take it to the p minus 2. It seems like it will take forever. It will take longer than just trying 7 times everything. The secret is that when you take a power, there is a very, very fast way to take a power. And this will be this will be an application of Fermat's little theorem to do something that we had seen before, now in a totally different way. I want 7 to the 17. How hard is that? I could just start multiplying. So let's start multiplying. 7 to the 1 is congruent to 7 mod 19. Okay, well, what's 7 squared? 7 squared is, it'll be 49, which, if I reduce mod 19, 19 is almost 20. So 40 is 2 more than a multiple of 19. Let me write that slowly. This is 2 times 19. That's almost 40. Plus, it'll be another 2 and 19. So plus 11, because that's 38. I mean, I knew it was close to 40. And there's a 9 here plus those extra 2. And this is then congruent to just 11 mod 19. Okay? Instead of doing 7 cubed, I want 7 to the 17. I'm not going to make 7 cubed. I'm going to make 7 to the 4th. You can use a method called repeated squaring, which lets you build a very big power very fast. 7 to the 4 now is just 11 squared, which is 121. If I need to reduce this mod 19, it looks like, because 19 is close to 20, it looks like it's 6 times 19. I'll even show you what's going on in my head. This is 6 times 19 plus 1, because 20 is 19 plus 1, and then plus another 1. So I already know that this is 7 mod 19. Okay, that's 7 to the 4th. If I have 7 to the 4th, I can get you 7 to the 8th, because that is the square of 7 to the 4th. And that is the square of 7, because I've showed that it's 7. Oh, I already did that. 7 squared is up here. So this is 11. Let's go to 7 to the 16. As you can see, I've gone all the way to 7 to the 16 in only essentially 5 lines. This is how fast it is to take a power if you use a binary style method. This is like the binary digits, 1, 2, 4, 8, 16. Because now I just need to take 11 squared. This is, again, 7 to the 8 squared, which is 11 squared. Oh, and I already have done that one too. 11 squared is here, 121. Actually, the fact that I already saw a pattern that I've seen before means it's just going to keep repeating. So this is going to be 7 mod 19. Okay, that's 7 to the 16. How do you get 7 to the 17? Well, you just multiply that by 7. So if I want 7 to the 17, I just have to multiply 7 times 7. It's 49. Let's do that. So if I want 7 to the 17, let me use this little space that's way up on top. 7 to the 17. I will write that as 7 to the 16 times 7 to the 1. I'm building 17 out of powers of 2. And that's going to give me 7 times 7, which is 49, which mod 19, I think I've already done. That's 11. Mod 19. Okay? This is, like this, the inverse of 7 mod 19. Really? That seems too good to be true. But, well, if you look at it, it works. I'm saying that if I take 7 times 11, well, that's 77. And 19, that's very close there. 19 times 4 is 36, 76. So we got the multiplicative inverse of 7 just by taking repeated squaring in order to make this work. You might ask, how difficult is this? What if I had to do this with a very large prime? Well, it only takes the log base 2 of that prime many steps in order to get there. Even if I wanted to get to 7 to the 128, that's only a few more lines. 32, 64, 128. That's how fast the repeated squaring is. Second question you might ask, what if I wasn't trying to get the 17th power? What if I want something else, like the 12th power? Well, the 12th power is just the 8th plus the 4th power. What I'm showing you is a trick for repeated squaring. And what it says is if I want to take any number, x, to some strange number, I will make one up right now, 35. All I have to do is break it apart into the powers of 2, the binary representation of the 35. X to the 32, x to the 2, x to the 1, and just multiply them together. And if you look at how we calculate these, you will get all of these powers of 2. So you can just choose the right ones and multiply together. So this gives a completely different way to find the multiplicative inverse of a number modulo a prime. One way which we showed was the Euclidean algorithm. That one works through addition and subtraction. This is using Fermat's little theorem. You don't need to prove Fermat's little theorem anymore. It's already been proved. If you use it, it just goes by straight multiplication all the way through. This mini course shows how lots of different concepts are connected to each other. We have modular arithmetic. We had multiplicative inverses, greatest common divisors. And in the end, the more pieces of the subject that you know, the more problems you can solve in more creative ways.